So let's do skill 3. Let's do 2 last examples from the exercises. I want to do number 11. This is kind of a similar type of question to the one that we just did in the last video, number 7. But rather than arc length, it has to do with the area. And so the idea here, right, if the total area of the circle is 114 square inches and the area of each blade is 6.6 square inches, what sector angle does each blade represent? So this is again sort of working off of the fan blade kind of setup that we had from the book example, just sort of taking that as kind of a generic area of a sector example. So we're changing around a little bit what we're asking, right? Again, rather than giving you a certain angle of rotation and having you find an area of a sector, we're giving you the sector area and wanting you to sort of unpack it and backtrack and find the angle of rotation that goes with it. So what have we got? This. The area is 114. The area of the sector is 6.6. So our formula, right, that connected these two together, the sector area should be the regular area times the angle over 360. If we start to sub the numbers in that we know, right, my sector area is 6.6. I'm gonna just sort of leave my units off just to simplify the look of it a little bit. We of course acknowledge always there are units that exist and they are important. So angle over 360. And in theory, this algebra is the exact same algebra setup from what we did in the last one. Just to change it up a little bit, what I'm actually going to do is change the order of how to solve it, just for kicks, just for fun, just to sort of show you guys something a little different. So what we did in the last one is we sort of said, well, 114 divided by 360, right? We could kind of do that math just on the right on its own, get kind of one number there and then go. You could also conceptualize this in some sense as, hopefully this isn't too confusing, but I mean, the version of this formula, this could really be written as a ratio, right? If you sort of have the area of the sector over the total area, it would be a ratio of the sort of angle that you're rotating through over 360, right? I think this kind of conceptually makes sense, right? However much your fan blade area is compared to the total area is going to be in sort of a direct proportion to whatever your sort of angle of rotation is over 360. So we can kind of solve it getting to this stage. The idea here is, well, do a division by 114 on both sides. These will then cancel out, right? 6.6 over 114 is, I don't know, 0.05789. Oh, we forgot about 6. 0.0, let's call that 0.058. Okay. And so that would be our angle over 360, right? So I just divided the 114 away. I divided it to the other side. I got another small decimal. You kind of get these decimals either way you do it here. It's not like we're going to do this one way or the other and avoid the decimals. They are what they are. How am I going to get rid of this 360 from the bottom? Well, now what I need to do is get it, I don't have a number here to divide, right? So I need to move this over, which means I'm going to cross multiply, right? I should multiply both sides by 360. That cancels this stuff from the right, and then I'm going to get, I guess I should use my rounded version, 360 times, oops, you guys can't see, sneak it up, 0.058 is what we're using rather than our long version, so 20.88 is my angle here. So 20.88 degrees of rotation for sort of each of those fan blades. Not a lot, right? But that kind of makes sense if they're only taking up, if the total area here was 114, and each of them individually is 6.6. There's obviously a pretty big difference between those two, so you'd expect this to be a relatively small angle. So same kind of setup, technically a different formula, but obviously the relationship there is very, very similar, and so the kind of solutions, or rather the sort of steps that you would take and the setups you have are conceptually effectively the same. It's just a matter of making sure you're using an area versus a circumference and going from there. The last one I want to look at from the exercises here is 15. So a car has tires with a radius of 9 inches. I know that nobody ever measures car tires by their radius, but go with it. How far will the car go in inches if the tire rotates 3 times? So let me write this information down. So this is 15. So my tire radius is 9 inches, right? It rotates 3 times, and so the question is, what is my distance traveled? That scribble was supposed to say traveled. So, okay, this is not really directly anything that we sort of had as an example before. This is something a little different, so we're going to have to sort of extend ourselves here. So what do we know? What's the actual connection here? Let's maybe do a quick little sketch, right? So here's a tire. Tire rotates, right? Radius is there. And so what's happening? So it rotates kind of 1, 2, 3 times, and it covers a certain amount of distance, right? And so the question is, how much distance does it cover? Well, what do we know? We know some angle stuff. So 3 rotations would be 3 times 360 degrees, right? That's going to be what? I think it's 1080. Yep. Okay. So is that helpful? Is this helpful, what I just found? Let's think about this for a second. So the tire rotates, right? I sort of said, kind of in passing in one of the other videos that, you know, our connection here, we said this sort of where the rubber meets the road saying, right, is, you know, as the tire rotates, what the sort of distances and the way these relationships sync up, right, is the distance around the edge of the tire, what would be our circumference, right? For every 1 rotation of the tire, the distance that you're sort of traveling, right, because the edge of the tire is what's touching the road. So every 1 rotation of the tire is going to cover 1 circumference's worth of distance on the road, right? So if I sort of say, okay, maybe, you know, from here to here, it's kind of 1 circumference, maybe here to here is like your 2 circumferences, and maybe from there to there is 3, right? So as that thing sort of rotates, if you think about this, if you've ever seen anybody like, you know, drawing, you know, painting the lines on the road, right, and using a little roller, right? If we sort of imagine this sort of covered in paint and we sort of rolled it, if we do 1 rotation, you're going to paint a line where the length of the line is the same distance as the circumference around the edge of the tire. So really what I've got here, I can do this 2 ways, I guess. You know, I can kind of conceptualize it and just say, okay, 3 rotations is 3 circumferences, right? Or I could do this as an arc length kind of thing. It's going to sync up with the distance around the edge. I guess either way we need the circumference, right? So let's find the circumference of this tire. We got the radius, so 2 times pi times r, 2 times 3.14 times my radius is 9 inches. What are we going to get? 2 times 3.14 times 9, 56.52 inches. Right, so that's my circumference. So any way I want to think about this, you guys can kind of write this any way you want. If you want to be very particular and think about it in terms of the arc length formula, you would say, you know, your length. So it's going to be that circumference times 1080 degrees of rotation over 360. You could also think of this as just 3 times the circumference. Either one of these, right? So 3 times 56.52 inches. Oh no, I didn't. I kept it on there, so that's convenient. So 169.56. Whoops. So my distance traveled would be 169.56 inches. So it's 3 rotations of the tire, meaning 3 circumferences. If I do 1080 over 360, that's going to reduce down to 3, right? So that's the connection between those two. And that's going to get me there. So that idea is going to come back into play in the next couple sections as we try to make some connections between tires rotating, in particular the rotational speed, right, RPMs, versus what we call the linear speed, which is sort of the miles per hour type speed that the car is traveling. So all this stuff is going to tie in here, a little bit of a conceptual sort of preview of things to come. And there you go, skill 3, all wrapped up.